Hello, everyone, and thank you all for being here. My name is Natalia.
And I'm Laasya. We're student researchers at Stanford focused on low-resource GPU kernel programming for AMD GPUs.
Today, we're really excited to talk to you all about adapting language models for HIP kernel programming, specifically how we can train smaller open-source models to generate faster correct kernels on AMD hardware.
Before we get started, I want to take a step back and talk about what kernels actually are. When people think about AI workloads, they usually think about the AI systems themselves. But underneath all of these models are low-resource kernels, are low-level instructions called kernels. Kernels are low-level programs written in AMD's HIP, which is AMD's GPU programming API. This middle layer, the kernel layer, is where performance is often won or lost. Even if two teams are training the exact same model, better kernels can lead to faster execution, better hardware utilization, lower power usage, lower cost, and overall better scalability.
We decided to focus on AMD's HIP, AMD's GPU programming API, for 4 big reasons. First was massive impact. AMD GPUs are becoming increasingly important across large-scale AI systems, and even small efficiency gains in the kernel can result in huge improvements in both cost and performance. Second was that HIP is open and portable. HIP is part of AMD's open ROCm software stack, so developers and researchers can inspect the tools and build on them. Also, AMD HIP is easy to adapt across different GPU setups. Third was the under-researched opportunity. Most of the kernel generation research that we read through focused almost entirely on NVIDIA's CUDA. And lastly was the low-level control. AMD HIP lets us get close to the hardware. We can directly reason about things like memory access, synchronization, and other low-level kernel-specific optimizations that are really important for performance. But writing kernels, HIP kernels, is also very hard. HIP is a low-resource language. There simply aren't that many open-source examples of high-quality HIP kernels out there. But at the same time, performance expectations are very high. Developers have to understand hardware behavior and performance trade-offs with limited guidance.
Take an example as simple as a matrix multiply. At first glance, it seems pretty straightforward, right? But writing a high-performance GPU kernel for a matrix multiplication is not a trivial task. Now we have to make decisions like, how many threads do we want to use, and how do we allocate work between them? How do we implement popular techniques such as tiling or fusion? And if we want to introduce synchronization, how can we prevent this from becoming a performance overhead? And if the underlying GPU architecture changes, how does the kernel have to change?
So naturally, people start asking, what if we use language models to help us generate correct and faster kernels? And at first, this sounds super promising. LLMs are good at generating code, recognizing patterns, and exploring lots of possible solutions very quickly. But kernel programming is different. The kernel needs to be correct and fast under very strict hardware constraints. Things like memory access, thread layout, and synchronization and low-level instructions all matter. So the real question becomes, can an LLM generate code that is not only syntactically valid, but also actually performant on the GPU? And one of the most important benchmarks for studying that question is Stanford's Scaling Intelligence's KernelBench. KernelBench starts off with 250 reference PyTorch implementations of machine learning workloads, ranging from single operators like gems all the way to full model architectures. Your language model of choice is then tasked to replace the PyTorch operator with a custom inline GPU kernel. The kernel is then evaluated in 2 ways. First, correctness. Was the custom kernel able to produce the same outputs as its PyTorch implementation? And the second is performance. How many times faster was the custom kernel in comparison to its PyTorch baseline? KernelBench and other recent works have shown that language models can generate and optimize GPU kernels, but they're limited. For example, They focus on NVIDIA's CUDA, rely on small fixed benchmark sets, and they also depend on these very large, expensive frontier models to generate the kernels.
Our work addresses these limitations through 3 key objectives. First, we synthetically generate over 500 new PyTorch tasks, spanning everything from single operators like gems to full model architectures to cover the AI workload space far more than what KernelBench can already do. Second, we translate and optimize each of these PyTorch tasks into HIP kernels using evolutionary search, multi-agent optimization, and we benchmark on real AMD MI350X GPUs. And third, we train small, low-cost open source models for kernel generation, with first, supervised fine-tuning on all of our synthetic kernels, and second, a GRPO-based reinforcement learning approach. For our study, we specifically focus on the Qwen Coder 14b model. Let's take a look at our multi-agent pipeline. Instead of asking just one LLM in a single prompt to do everything in the kernel engineering process, we break it up into specialized steps and assign an agent for each of them. Let's start with our task generator, whose goal is to generate all the synthetic PyTorch reference modules. Let's take a closer look at that.
Our first method for generating the synthetic data is mutation. Here, instead of asking the model to generate an entirely new workload from scratch, we leverage the existing KernelBench problems. We take an existing problem and we produce a variant of it, or a mutation of it. Here, for example, we could take a matrix multiplication with a bias add and a ReLU activation function and we mutate it. You can see 4 different examples of that here. The first one being that we mutated the operation itself, swapping the matrix multiplication with a batch matrix multiplication, and the last one being that we mutated the activation function. This keeps the general structure of the KernelBench problems while also requiring different optimization strategies. Our second one is composition. Here we are generating entirely new problems from scratch. We fuse operations together from an operator template library, which contains 14 different operations. Some of these can contain layer normalization, softmax, and matrix multiplication, and we give the model a single instruction. Compose these into a single PyTorch module and ensure compatible shapes. And the resulting module is an entirely new problem. And because we are sampling from the same opset with different candidates, different output operations, and different shapes, we get an entirely diverse data set.
Our last mode of generating synthetic data is constraint. Unlike the previous 2 approaches, mutations and compositions, constraint doesn't depend on a pre-existing PyTorch module. Instead, we're using a natural language description. For example, here, as a developer, I could ask, I want to create a kernel for a batch gem with a layer norm and GLU, and the shape should be divisible by 8 with floating point 16 precision. From there, the agent has to understand the natural language description, plan the different operations, build the PyTorch structure, and finally generate the code. And here, again, we're not going to restrain the model too much. As long as it follows the task description, specifically the shapes and the precision, it's open to generating more diverse kernels. And across all 3 of these methods, mutation, constraint, and composition, we're running a forward pass on the PyTorch reference modules so we can make sure it generates valid outputs. Great. Now that we've covered all 3 methods of our synthetic data generation, let's go back to our multi-agent pipeline. The most important agent on the slide here is the translator, whose sole purpose is to take all of the synthetic tasks we just created and create valid HIP kernels for them that are correct. From there, we have a hard verifier and a hardware evaluator. And the goal of both of these agents is to 1, compile the kernel, 2, get a baseline runtime measurement, and 3, check if it's correct. From there, the most important agent we're introducing is our evolutionary optimizer. The goal of the evolutionary optimizer is once we have a correctly compiled and a correct output kernel, we want to make it faster and more performative. And so the evolutionary optimizer, instead of just increasing the performance of one kernel at a time, we're actually going to leverage massive parallel search and explore various generations of candidates in order to get the fastest kernels. Specifically, in this approach, our evolutionary optimizer agent is going to be using a Sakana AI-style approach to search its own archive of previously verified kernels that are either performant or similar to the current task description. It'll then retrieve these examples and inject them as in-context examples for the next iteration. After we have this set of kernels that are potentially more performant, we run 3 different steps. First, a soft verifier, which is a cheap LLM-based pre-screen to basically flag out any obvious compilation or memory issues before using expensive GPU time. Then we push it to, again, our hardware evaluator and our hardware verifier to get stats on our runtime, compilation, and correctness before feeding all of this information back to the evolutionary optimizer and asking it to make it go faster. Across this entire orchestration, we're collecting so much data. Every single kernel that's generated is stored, as well as its runtime measurements, correctness results, and compilation results.
Once we had this large set of synthetic data, our next question was, how do we actually use these to improve the model? With supervised fine-tuning, we trained the model on correct kernels, so it learned the general structure of what correct, good HIP code looks like. But we wanted the kernels to be not only correct, but also offer speedup. So we turned to reinforcement learning for this problem. Specifically, we implemented GRPO, which is Group Relative Policy Optimization, and we built on the Dr. Kernel paper, which is a 2026 study that implements RL for Triton kernel generation. Here's how it works. At each training step, the model gets a prompt. Write a fast kernel that accomplishes this operation. The model then generates a group of candidates. Each candidate is compiled and run on AMD GPU. It's rewarded based on whether it compiled, whether it was correct, and how fast it was relative to its PyTorch baseline. In standard GRPO, each kernel is compared against the mean reward of its group. To solve this problem of self-inclusion bias, we also used Dr. Kernel's turn-level reinforced leave-one-out idea. In addition to that, we also incorporated 3 of our own key techniques. One of them is multi-turn RL, inspired by the Kevin paper on multi-turn RL for NVIDIA CUDA kernels. Second was reward smoothing. We tracked the last 100 rewards and clipped unusually high or low values when computing the advantages. And lastly is a summarizer agent. Like Laasya mentioned, every time the optimizer failed, we tracked exactly what went wrong. We ran this data against a summarizing agent that condensed these into shorter lessons for the model to learn about past mistakes to avoid.
Let's take a closer look at this reward policy. Following the motivations of the Dr. Kernel paper, there are 2 key reasons for kernel failure. One is compilation results and correctness results if they fail to compile or they produce incorrect outputs. And the second is lazy optimization. We followed the Dr. Kernel reward policy as follows. If kernels fail to compile, we give the model a -1 reward. If they produce the wrong output, we give them a -0.5 reward. And from there, every kernel that is both correct and compiles scales its reward with how performant it is. And we cap this reward at 4 points. The first metric we measured is compilation rate. And the 3 environments that we're studying is our baseline Qwen 14B coder model, our supervised fine-tune model on all our synthetic data, and finally, our custom GRPO reinforcement learning approach. As we can see in our data, across level 1, level 2, and level 3 problems, we're significantly increasing in compilation rates from baseline to SFT to RL. Upon taking a closer look, we were interested to see why the baseline did so poorly. And what we found was that although the kernels looked like valid HIP code, they often reflected a deeper misunderstanding about generating HIP. For example, invalid memory access or shape mismatches. From there, after the SFT, we saw that the kernels for this mode of our environment actually started to produce some correct patterns because it was trained on all our correct kernels. And finally, with the reinforcement learning, we again see a jump in compilation rate solely because we're actually rewarding compilation on real hardware GPUs. The next metric we look at is correctness rate. And again, across all three environments, we're seeing improvements from the baseline to SFT to RL. Specifically, we expect to see this jump from SFT to RL because, again, we're directly including correctness as part of our reward signal. We were interested to see how big of a jump we got in level 2, though, from SFT to RL.
We then looked at FastP, which is a metric developed by KernelBench and measures the percentage of kernels that are correct and offers a speedup of p times over its PyTorch baseline. Here we can see the FastP values for SFT. At lower speedup thresholds, we see a reasonable number of correct kernels that were generated. But as this speedup threshold increases, that number drops drastically. And so we can reason that while supervised fine-tuning allowed for it to learn the general structure of correct kernels, that speedup optimizations were needed. So let's now look at reinforcement learning. We can see here that the reinforcement learning results are much higher. Because GRPO directly rewarded speedup, we see an increase in the percentage of correct kernels as the speedup threshold increases, especially for level 2. We can reason that this is because of our composition synthetic data, which fuse together multiple operations that is reflective of the level 2 tasks in KernelBench. However, it's also important to note that kernels that were correct did not surpass a speedup threshold of 1x. And this shows that the model needs a deeper understanding of GPU architecture and parallel execution than was captured in the training data.
To wrap up our contributions, in this work, we explore adapting language models for low-resource GPU kernel programming. We are contributing to this space in 3 main ways. First, we're expanding the problem space itself. We're going beyond the fixed 250 tasks, PyTorch tasks that KernelBench curates, and we develop an entire synthetic data pipeline, including mutation, composition, and constraint-based task variation. From this, we're expanding to all sorts of different AI workloads beyond, again, what KernelBench can include. Our second contribution is our multi-agent optimization pipeline. Instead of asking just one LLM to do everything in the kernel engineering process, we divide and allocate to different agents, including an agent to create all our synthetic data tasks, an agent to actually create correct HIP kernels, and our evolutionary search optimizer, which is going to search for faster HIP kernels. And our final contribution in this space is we're taking all of this data and we're actually doing supervised fine-tuning and our GRPO-based reinforcement learning for HIP kernels. As we saw in our results across compilation and correctness from level 1, level 2, and level 3, we significantly saw performance gains, specifically from RL. From here, we look forward to really working on the performance gains and specifically integrating the RockM profiler so we can learn from more direct hardware feedback.
We would like to sincerely thank AMD and especially Aman and Sharon for their support in providing us with compute to make this research possible. We would also like to thank Anne Maria, Simon Guo, and Dr. Azalea Mir-Hosseini from Stanford's Scaling Intelligence Lab for their mentorship throughout this research. Thank you so much.
Thank you all so much for joining us today.